So we're discussing this Ribbling-Erection theorem. So I have already proved it in the trivial direction. So now today we will do the proof for the Ribbling-Erection theorem in the non-trivial direction. So let me just write this G of S, that is equal to P naught of I of S times I plus P1 of I of S times S plus P2 of I of S times S squared. Okay, so this is the characterization for the tensor valued isotropic function G. So we want to show that if G is a tensor valued isotropic function, then it has to have this particular form. Okay, so as I said, this proof is fairly non-trivial. Okay, so proof of the converse now. So proof. Okay, so assume now that G is isotropic. Assume that G is isotropic. So that means G of Q S2 transpose is equal to Q G of S times Q transpose. Okay. So first we'll prove that every eigenvector of S is also an eigenvector of G of S. See, this is generally to show that eigenvectors are the same is generally very difficult, because to show that eigenvalues, suppose if they were the same, to show that eigenvalues are the same is generally a little bit easier, because all you have to do is show that the characteristic equation is the same. But whenever you want to show that the eigenvectors are the same, that is not so trivial. So in this particular case, the eigenvalues are not the same, but the eigenvectors between S and G of S are the same, and so as I said, that proof is not so trivial. So let us start with the spectral decomposition of S. So that is EI star dyadic EI star. So since S is symmetric, we can write it in the spectral way in this particular form, and let Q be the tensor that diagonalizes S. Okay, so let Q be equal to E1 dyadic E1 star plus E2 dyadic E2 star plus E3 dyadic E3 star. So this belongs to orth plus. We have already seen that tensors of this form are proper orthogonal, and this E1, E2 and E3 is the canonical basis. Okay, E1, E2, E3 is the canonical basis. So by canonical, I mean the 1, 0, 0, 0, 1, 0 and 0, 0, 1. So that is the canonical basis. So you can think of this that this Q is formed using the eigenvectors of S along the rows. Okay, so you can think of it in this particular way. But I am writing it in the tensorial form also here. And so if I now find Q times S times Q transpose, so then we will see that that is equal to Q times summation lambda I EI star dyadic EI star times Q transpose. Okay. And this can be written as equal to summation of EI dyadic EI star times summation of lambda I times EI star dyadic EI. Okay, so just do after a little bit of manipulation, this is what you get. So this actually is Q itself. So this here is Q, and this part is this lambda EI star dyadic EI star times Q transpose. So that is this particular part here. So this, if you now multiply it out, you will get that this is lambda I EI dyadic EI. Okay? And so this is just a diagonal matrix with lambda 1, lambda 2, lambda 3 on the diagonal. So, I mean, all we have shown is that Q, this particular tensor Q, diagonalizes S. That's all that we have shown so far. Now, let us take two special proper orthogonal tensors, and so now this part of the proof is the sort of clever part of the proof here. So we now consider two proper orthogonal tensors in the following way. So this is Q1 is equal to E1 dyadic E1 minus E2 dyadic E2 minus E3 dyadic E3. So this is actually nothing but the 1 0 0 0 minus 1 0 0 0 minus 1. So this tensor is just with minus 1 on the diagonals in the 2 2 position and the 3 3 position here. And then Q2 you write as Q2 you assume to be minus E1 dyadic E1 plus E2 dyadic E2 minus E3 dyadic E3. So this tensor is just with a minus 1 0 0 0 1 0 0 0 minus 1. So this is this has a minus 1 in the 1 1 and the 3 3 position here. Right, now we will make use of these Q1 and Q2 in the following way. So first you should note that Q1, Q2, then Q1, Q and Q2, Q, they are all proper orthogonal tensors here, right? So this can be easily verified. Just verify that the transpose is the inverse, right? And then also the determinant should be equal to plus 1. So that is very easy to verify for these two, for all these tensors that I have written here. Fine. Now we also have that Q beta times Q S Q transpose times Q beta transpose is equal to summation lambda I times EI dyadic EI, which is also equal to Q S Q transpose. If you so this Q S Q transpose we have already found out, right? That is this lambda I times EI dyadic EI, and if you pre and post multiplied by Q beta transpose, you will see that you will get back the same tensor. That is this Q S Q transpose. So this is for beta equal to 1, 2. So for both, I mean, if you take Q1 and Q1 here, or you take Q2 and Q2 here, you will get back Q S Q transpose here. Right now, so now let us use the fact that G of S is an isotropic tensor. So yes, so by the assumed property of isotropy, you will get that Q beta times Q G of S times Q transpose times Q beta transpose is equal to G of Q beta S, Q S Q transpose Q beta transpose. So because this is a proper orthogonal tensor, so that can be taken inside, right? Because we have that Q times G of S times Q transpose is equal to G of Q S Q transpose, right? So because of this particular property, now whatever is outside, if they are proper orthogonal, they can be taken inside. So that is what we are doing. And then again use the property of isotropy. So this can, so first you first you will use the fact that this Q beta Q, all this is just Q S Q transpose. So this is G of Q S Q transpose, and this is equal to Q times G of S times Q transpose. Right? So you can write it in this particular way here. Okay, then if you actually now consider this particular object here, so that is QG of S times Q transpose that is occurring on both sides in this particular case. So if you now take any symmetric tensor and if you pre-multiply it by this Q beta, that is Q1 and Q2 on both sides, then you will get that this is a diagonal tensor. Okay, so so this is just a sort of brute force calculation that you can carry out, and then you will see that. So basically, if you have Q beta times S11, S12, S13, and so on up to S33 times Q beta is equal to S11, S12, S13, and so on up to S33. Okay, so I'm just using this S11, S12 for this whole object here. So then you will see that this S12 is 0, S13 is 0, and so on. If you write it out, you will find that. Okay, so this will imply. So this is for both. I mean, you will have to use both these tensors, beta equal to 1, 2. Then you will get that S12 is equal to S13 equal to S23 is equal to 0. Okay, and so basically it is a diagonal tensor. So that is what we have now shown. So so now this implies that Q of G of S times Q transpose is diagonal. Okay, so what does that mean? So that means that Q was the tensor that diagonalized S, and it is also the tensor that is diagonalizing G of S. Hence, their eigenvectors must be the same. Okay, so that's what we have now shown. So that so hence the eigenvectors of S and G of S are the same. Okay, so that is the. So that actually, so this is the really clever part of the proof. Okay, so identifying these tensors Q1 and Q2, which will show that the eigenvectors of S and G of S are the same. So this actually is the clever part. So after this, it is more or less a routine exercise now after this particular point. Once we show that the eigenvectors are the same, then after this it is more or less a routine calculation. So this is the heart of the proof, to show that the eigenvectors of S and G of S are the same. Okay. Now, so hence now we can write G of S is equal to mu1 times E1 star, that is E1 star plus mu2 times E2 star, that is E2 star, plus mu3 times E3 star, that is E3 star. So the eigenvalues can be different. So we had denoted the eigenvalues of S by lambda 1, lambda 2, lambda 3. So here I will call the eigenvalues of G of S as mu1, mu2, mu3 in this particular case. So now we need to show that we'll show that G of S can be written as equal to alpha naught of S times identity plus alpha 1 of S times S plus alpha 2 of S times S squared. So we'll show that this tensor can be written in this particular way. So for all S belonging to P sim. So for all S belonging to P sim. Okay. So let us show this. Okay. So this first assume that lambda 1 not equal to lambda 2 not equal to lambda 3 is not equal to lambda 1. So we first assume that the eigenvalues of S are distinct. Okay. Then so then the sets E1 star, that is E1 star, E2 star, dyadic E2 star, comma E3 star, dyadic E3 star. So if you take the linear span of this, that is equal to the linear span of I, S and S square. So why is this true? So let us see why this is true. So first of all, this E1 star, E2 star, E1 star dyadic E1 star, E2 star dyadic E2 star and E3 star dyadic E3 star are linearly independent. Okay, so E1 star dyadic E1 star, E2 star dyadic E2 star, E3 star dyadic E3 star are linearly independent set. Linearly independent set. So that is just, you can use the usual method of figuring out whether something is linearly independent or not, plus alpha 2 E2 star dyadic E2 star plus alpha 3 E3 star dyadic E3 star is equal to 0. Right? We start with this and we need to show that alpha 1 equal to 0, alpha 2 equal to 0 and alpha 3 equal to 0. So if we are able to show that these three things are 0, then E1 star dyadic E1 star, E2 star dyadic E2 star and E3 star dyadic E3 star are linearly independent. Right? So here, just if you take the dot product, so operate on this thing with E1 star and take the dot product with E1 star. Right? So then this will imply that alpha 1 is equal to 0. Right? And then in the same way, you can show, that alpha 2, so similarly alpha 2 is equal to alpha 3 is equal to 0. Okay, so that just by operating, so just multiply this whole equation by E1 star and take the dot product with E1 star, then you will get that alpha 1 is 0. Similarly, alpha 2 and alpha 3 are also 0. Yes. Okay. So basically, this is a three-dimensional subspace of the space of symmetric tensors. Right. So this here is a three-dimensional subspace of the space of symmetric tensors. Right. Okay. And so it's a vector space itself. And then we will now express this I, S and S square in terms of this E1 star, E2 star and E3 star. So you will get now I is equal to E1 star dyadic E1 star plus E2 star dyadic E2 star plus E3 star dyadic E3 star. Then S is equal to lambda 1 E1 star dyadic E1 star plus lambda 2 E2 star dyadic E2 star plus lambda 3 E3 star dyadic E3 star, and S square is equal to lambda 1 square E1 star dyadic E1 star plus lambda 2 square E2 star dyadic E2 star plus lambda 3 square, this is 3 here, and E3 star dyadic E3 star. Right? So this, if you recall that theorem which we have, where we had Fi is equal to beta ij ej, right? This was the theorem that I did for the figuring out whether a set Fi is a basis or not. So at that time we saw that Fi is a basis, right, for an n-dimensional vector space if determinant of beta ij is not equal to 0. Right? Here we had that condition that determinant of beta ij, if that is not equal to 0, then Fi is also a basis. So here this is exactly the same. So here if you write what is this Fi, then that is just the matrix of coefficients here, right? Sorry, the beta ij's. So here the beta ij's matrix in this particular case is nothing but this matrix of coefficients here, that 1, 1, 1. So that is 1, 1, 1. Then lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3, and lambda 1 square, lambda 2 square, and lambda 3 square. Lambda 1 square, lambda 2 square, lambda 3 square. Right? And then we have assumed that this lambda 1, lambda 2, lambda 3 are all distinct. Right? So you will get the determinant to be a non-zero quantity here. So determinant of this, so let me just write it here. So determinant of beta ij is equal to the determinant of this matrix. So that is equal to lambda 1 minus lambda 2 minus lambda 3 times lambda 3 minus lambda 1, which is not equal to 0. Okay. So because the lambda 1, lambda 2, lambda 3 are distinct, hence the determinant is not equal to 0. Hence now we can say, so just exactly from this theorem, right? So if EI is one basis and if the determinant of the beta ij is not equal to 0, Fi is also a basis. So in the same way, now this IS square is also a basis for this three-dimensional vector space of that spans E1 star dyadic E1 star, E2 star dyadic E2 star, and E3 star dyadic E3 star. So what basically now what we have proved is this particular statement here, that the linear span of these three members is exactly the same as the linear span of Is and S square. And so now we can write the G of S in the way that I had written earlier here. So because we have now shown this particular relation here, that the linear span of these three bases is equal to the linear span of I, S and S square, we can now write G of S as equal to alpha naught of S times identity plus alpha 1 of S times S plus alpha 2 of S times S square for all S belonging to P set. So you can write it in this particular way now. Fine. Now, but we need to show that this even for the case where the eigenvalues are repeated also. So now let us take the second case, which is that lambda 1 is not equal to lambda 2 is equal to lambda 3. Okay, so then now the two eigenvalues are repeated. Now we will show that the two sets I, S and E1 star dyadic E1 star comma E2 star dyadic E2 star plus E3 star dyadic E3 star span the same space. Okay. So we will show LSP of this is equal to LSP of this object. So that is what we need to show. So in this particular case, you can write that I now is equal to E1 star dyadic E1 star plus E2 star dyadic E2 star plus E3 star dyadic E3 star, right? And so you can see that this is one object, and then S is equal to lambda 1 E1 star dyadic E1 star plus lambda 2 times E2 star dyadic E2 star plus E3 star dyadic E3 star. And so you can see that this object is the same in both of them, and hence if you take now the determinant of the coefficient matrix, so determinant of 1, 1, lambda 1, lambda 2, so this is equal to lambda 2 minus lambda 1, which is not equal to 0. And hence again, we can see that linear span of Is is equal to linear span of these basis vectors here. Fine, so now for this particular case, we need to show that the eigenvalue corresponding to this E2 star and E3 star is also repeated, okay, for G of S. So that we need to show. So G of S we will write as G of S times E2 star is equal to mu 2 times E2 star. So this is because the eigenvectors of S and G of S are the same, correct? So if E2 star is an eigenvector of S, then it is also an eigenvector of G of S. And similarly, E3 star is also an eigenvector of S and G of S, and any vector, in fact, in the plane of E2 star and E3 star is an eigenvector of G of S. So here let me just state that any vector in the plane of E2 star, E3 star is an eigenvector, right? Eigenvector of G of S. And so first I will take it as E2 star, and then I will take E3 star also as one of the eigenvectors. So this is equal to some mu3 times E3 star. So we cannot assume now. So we are trying to show that mu2 is equal to mu3. So we cannot assume that these eigenvalues corresponding to the repeated eigenvalue of S, this mu2 and mu3, they are the same. We cannot assume that. So we are trying to show that particular thing. And as I said, that any vector in this plane is an eigenvector. So if I take G of S times E2 star plus E3 star, so that also is an eigenvector. You can suitably normalize it if you like. So that is equal to mu now times E2 star plus E3 star. And then by the linear independence of the E2 star and the E3 star, you will see that this whole thing now, so this implies that mu is equal to mu2 is equal to mu3. So basically what we have shown is that if the eigenvalue of S is repeated, then the corresponding eigenvalue for G of S is also repeated. Okay, and then that we are just calling as mu. So now because of this, we can now write in the following way now. So we can write it as G of S is equal to mu1 times E1 star, that is E1 star plus mu2 times E2 star, that is E2 star plus E3 star, that is E3 star. So now since the eigenvalue is repeated, I am just using this mu. Or let me just call it as mu. What is that? Mu is equal to mu2 is equal to mu3. So let me just call it as mu here. And then we have shown that this and this together, the span of this is equal to the span of I and S. So hence I can write here in this particular case, G of S is equal to alpha naught of S times identity plus alpha 1 of S times S for this particular case here. Now the third case is when all the eigenvalues are repeated. Lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to lambda. So in this particular case, any vector, right, is an eigenvector for S, and so any vector is also an eigenvector for G of S, right, in this particular case. So all unit vectors are eigenvectors, of S, and hence of G of S. And so hence G of S is equal to some multiple of the identity tensor, and then again using similar arguments as here, we can write this as alpha naught of S times identity tensor here, right? So in all three cases we can write it as G of S is equal to alpha naught of S times identity plus alpha 1 of S times S plus alpha 2 of S times S square in all three cases, because so whenever the eigenvalues are repeated, then this alpha 2 can be taken to be 0. When if all the three eigenvalues are repeated, then this alpha 1 also can be taken to be 0, but they all fall under this particular representation here. Yes, so now the last thing now to be shown is that these alpha naught, alpha 1 and alpha 2 are actually functions of the principal invariants of S. So again we will use the assumed property of isotropy in order to show that. So that is the last step in this particular proof here. So G of QS Q transpose is equal to Q of alpha naught of QS Q transpose times identity plus alpha 1 of QS Q transpose times S plus alpha 2 of QS Q transpose times S squared times Q transpose. Right? You can write it in this particular way. So I've used the fact, just basically wherever S occurs, I am simply substituting it by QS Q transpose. And this is also equal to Q times G of S times Q transpose, and which is now equal to, so this actually is the assumed property of isotropy, and this is also equal to Q times alpha naught of S times identity plus alpha 1 of S times S square, S plus alpha 2 of S times S square times Q transpose. Right? And now if you compare these two, right, then now these I, S and S square are linearly independent, right? So depending on whether the eigenvalues are repeated or they are distinct, right, these three are linearly independent, and so we can directly equate these coefficients here. So this implies now by the linear independence of I, S and S square, we can write this as alpha I of QS Q transpose is equal to alpha I of S. And so basically these alpha I's, so this is for I equal to 0, 1, 2. So these alpha I's are scalar valued isotropic functions. So this now implies that alpha I is equal to, let us call it as Vi of I of S. Right? And so that proves the theorem. Right? So basically now we can replace, so in this particular thing we can now replace, so now here we can replace this I phi naught of invariance of S times identity plus phi 1 of the invariance of S times S plus phi 2 of the invariance of S times S squared. So that proves the Ribbling-Erection theorem. So if so to summarize now, if G of S is a tensor valued isotropic function, then it has to have this particular form. Right? So that is the idea. All right. So actually, at this stage, it is just a mathematical theorem. At a later stage, we will apply this to characterize the constitutive relation for an isotropic material. So actually, it would have been a very, very useful result in a practical context had these things also been more sharply defined. But as you can see, that they can be any function of the invariance, right? And so although this I, S and S square is very sharply defined, but this can be any invariant, and so in some sense finally it does not help much when we are trying to characterize isotropic materials. So in the sense that still trying to match it against experimental data, we still need to guess what these forms are. In any case, we will come to that at a later stage. At this stage, we will not worry about that, but I'm just pointing out that that invariants, they can be of any form. The phi naught, phi 1 and phi 2 can be of any form there. Okay, then now let us look at the representation theorem for linear isotropic functions. Okay, representation theorem for linear isotropic tensor functions. So actually it may appear that one can just get this theorem as a corollary of the previous theorem, right? But somehow that is not very trivial to show, because as I said, the phi naught, the phi 1 and the phi 2, we do not know what their forms are, right? And so it becomes extremely hard to derive this particular result as a corollary of the previous theorem. So what we will do is that we will give an independent proof of this particular theorem. So a linear function g of s from sim to sim is isotropic if and only if there exist scalars lambda and mu such that g of s is equal to lambda trace of s times identity plus 2 mu times s for all s belonging to sim. So again, in one direction, so if you are given this particular form, then it is obvious that this is a linear form in the sense that g of alpha 1 times s1 plus alpha 2 of s2 is equal to alpha 1 of g of s1 plus alpha 2 g of s2. So it is obvious that it is linear because trace is a linear operator and then this s is obviously linear in s itself. So it will satisfy this particular property, and so the fact that it is linear and an isotropic function is obvious, right? But we want to show that this is the only form that it can assume if we have a linear isotropic tensor valued function. So let us prove this, the proof of the converse, right? So I'll just prove the non-trivial part in this proof here. So here let V1 be the set of unit vectors, right? Let V1 be the set of unit vectors, and for E, so some vector E, okay, which belongs to V1, the tensor E dyadic E has eigenvalues 1, 0, 0 or 0, 0, 1, 100, 0, 0, 1. So that is there are several ways to show that the eigenvalues of E dyadic E are 0, 0, 1. The easiest way is that you set up an orthogonal transformation between E dyadic E and E1 dyadic E1. So suppose E1 dyadic E1, so where E1 is the canonical basis, so the matrix representation of E1 dyadic E1 is 1, 0, 0, 0, 0, 0, 0, 0, 0, right? And the eigenvalues of this is 0, 0 and 1. And then you can now multiply it by some Q transpose, and then you can get E dyadic E, right? You can always find an orthogonal tensor such that Q times E1 dyadic E1 times Q transpose is E dyadic E. And then because they are orthogonally equivalent, the eigenvalues of E dyadic E are the same as the eigenvalues of E1 dyadic E1, which is 0, 0, 1. So there may be several ways of proving this, but this is just one method of proving this. So basically here you will see that two of the eigenvalues are repeated. So now we go back to the previous proof, okay, and then we can write now. So go back to the previous proof. So since two eigenvalues are repeated now, so since two eigenvalues, so this is the second case in the Ribbling-Erection theorem's proof, right? So since two eigenvalues are repeated, we can write this as G of E dyadic E is equal to lambda of E times identity plus 2 mu of E times E dyadic E. So this is that case where we wrote alpha naught of S times I plus alpha 1 of S times S. So if you go back to that particular case, the second case where two of the eigenvalues were repeated, then we had shown that the representation is in this way, right? So here this is exactly that. So there it was G of S had this representation. So now I can write G of E dyadic E has this particular representation. So this basically S is E dyadic E in this particular case here, right? So now choose these E and F now. So choose E and F belonging to V1, and let Q belonging to R plus, such that F is equal to Q times E. So basically F is just a rotated version. So if this is E, then QE, so this is F, so I'm just calling it as QE, which is, so F is just a rotated vector, rotated version of E itself. Right, now we will use this isotropy again, the isotropic property of G of S. So Q now of E dyadic E times Q transpose is equal to QE dyadic QE. So this is just a usual property of dyadic products, and this can be written as F dyadic F. Okay, then now we'll use the isotropic property. Since G is isotropic, we'll get that so 0 is equal to Q times G of E dyadic E times Q transpose, which is minus G of F dyadic F. Right, so that is because of this property. So you can always take this Q inside, right, because it is isotropic, and then Q of E dyadic E times Q transpose is equal to F dyadic F. So it is G of F dyadic F minus G of F dyadic F, which is 0. So we can write it in this particular way here. And now use the representation here. So this G of E dyadic E is lambda E times I plus 2 mu times E dyadic E. So this will give me, so this is equal to lambda of E minus lambda of F times identity plus 2 times mu of E minus mu of F times F dyadic. So I can write it in this. So all I have done is that I have just simply substituted for G of E dyadic E and G of F dyadic F using this particular representation, and then you will get this particular result here. Now, since I and F dyadic F are linearly independent, the coefficients have to be equal to 0. Correct? So since so that actually you can simply so what you can do is multiply both sides by some G, okay, where this G is perpendicular to F. Okay, so what will happen is this will become F dot G, which will be 0. So F dot G is equal to 0, right? And then you will get a G here, and so lambda E has to be equal to lambda F. So this implies that lambda E is equal to lambda F, and then once lambda E becomes lambda F, this part goes to 0, so mu E has to be equal to mu F. So this then in turn implies that mu E is equal to mu of F. So basically what we have shown at that these lambdas and mu's are constants. That they do not depend on the vectors E and F. So lambda and F are constants. So this implies, so together lambda mu are constants. Right? So okay. So we can now simplify that particular expression here. Fine. So now we have that G of E dyadic E is equal to lambda times identity plus 2 mu times E dyadic E. So where now, so now the difference from the previous expression is that now these lambda and mu's are constants. Previously they were functions of E, so now they are no longer functions of E, they are just constants here. Right, now we have still not used the linearity of G of S. So now that will come in. So if I now write S as equal to summation of alpha I, Ei star dyadic Ei star, then G of S is equal to summation of alpha I times G of Ei star divided Ei star. So here, this is where I use the linearity. See, the alpha I comes out of this G of Ei star divided Ei star. So this is the place. So up to now I had not used the linearity. I just used the fact that G of S is a tensor valued isotropic function. But this is where I use the linearity now. So this is I equal to 1 to 3. Okay, and then this I can write as E equal to. So use this result now. So substitute G of Ei star divided Ei star, that will be lambda times I plus 2 mu times Ei star divided Ei star. So if you substitute that, what you will get is that you will get lambda times alpha 1 plus alpha 2 plus alpha 3 times identity plus 2 mu times S. Right? And then alpha 1 plus alpha 2 plus alpha 3 is nothing but trace of S. Right? This is trace of S itself. So we get the result. Finally, what we get, let me just write it here. So finally we get the result, that whatever we are trying to prove here. So from here you will get that G of S is equal to lambda times trace of S times identity plus 2 mu times S. And so that is what we wanted to show. So as I said that trying to prove this as a corollary somehow does not work, but this is just an independent proof of this particular fact here. Okay, so we will move on. Now we'll start with a new topic. So this completes the portion on isotropic scalar valued and also isotropic tensor valued functions. So actually this is a very vast field in the sense that we have considered only one tensor argument. So an isotropic function of one tensor argument. You can have functions that are or isotropic functions of one tensor and a vector, or one tensor and another tensor, and so on and so forth. So it's a very vast field, but essentially I have just proved the results that I will require for this particular course. Yes, so now let us start with differentiation of tensors. So this is again a new topic now, differentiation of tensors. Yes, so I will write f of u, write f of u is equal to order u if limit of u tending to 0 of f of u, the norm of that by norm of u is equal to 0. So this is exactly like in a Taylor series we write order of epsilon square, right? So this is exactly the same way. So this is the same order that we write in a Taylor series representation. So and defined in this particular way here. So generally we are familiar with the ordinary derivative concept, but when we are dealing with tensors, we need to introduce the directional derivative. So just the ordinary derivative does make sense, but the directional derivative is the derivative in a particular direction. Okay, so we'll now make this more precise here. So directional derivative. So this directional derivative is very, very useful when you are carrying out linearizations of tensorial quantities here. Yes. So first let us just talk about the usual derivative of a function, right? So let g be either scalar valued, scalar vector, or tensor valued, or tensor valued function. Okay, then the domain is just R itself. Okay, so basically G is a scalar vector or tensor valued function of a scalar variable t, let us call it. Okay, so d of g of t, that is just the ordinary derivative. So dg by dt. So this is all of you are familiar with this. This is just from calculus, ordinary calculus. So this is 1 by alpha of g of t plus alpha minus g of t, right? As in the limit as alpha tends to 0, and I can write it in an alternative way. You can write this as alpha tending to 0 of 1 by alpha of g of t plus alpha minus g of t minus alpha dg of t. Right? So this is can write it in this particular way also, right? Or yet another way to write this would be like a Taylor series. So g of t plus alpha is equal to g of t plus alpha dg of t plus order of alpha. So this order of alpha is exactly whatever this order of u. So that is the same thing. So that means terms that involve alpha square, alpha cube, and so on here. Yes. So now our idea is to generalize this concept to higher order domains. Okay, so here G itself is scalar, vector, or tensor value, but the domain I had considered was just a scalar, right? So now the idea is that we will extend this to domains that are of higher order. So let us do that. And so for that we need to introduce the concept of a directional derivative. Yes, so let us do that now. So yes, so we say that G is differentiable at x belonging to some omega if there exists a linear transformation d, we'll call it as d of g of x, such that g of x plus u is equal to g of x plus d of g of x in the direction u plus order of u. So this part here, this d of g of x in the direction u, is known as the directional derivative. So this is the directional derivative, directional derivative, and or the Gattau derivative. And the actual this part alone, right, the dg of x, that is known as the Frechet derivative. D of g of x is known as the Frechet derivative. So this this x that I am writing here need not be a position vector. Okay, so this, so this is just in some space. Okay, it could be the space of vectors, it could be the space of second order tensors. So, but this is the general definition of a directional derivative. So maybe many of these things will become clear when I actually give you some example of this one. So this you can also write this directional derivative in another way using this. So this d of g of x in the direction u is equal to limit. So just like in the previous case, we had this limit definition. So I can write it in that way also. So this is g of x plus alpha u minus g of x. Or alternatively, I can also write this as d by d alpha of g of x plus alpha u evaluated at alpha equal to 0. You can also write it in this particular way. So these are all various ways in which you can define the directional derivative. So basically it is like a first order term, and so since it's a first order term, it is linear also, right, in u. So that is the important thing to remember in this particular case here. Yes, so let me just simplify these things here for yes, so so if now if you go back to the case where the domain is the space of real numbers, then let us see what happens here. So when omega is a subset of R now, then what happens? Then I can write it as let's see, so I have written that g of t plus alpha is equal to g of t plus alpha times d of g of t, right? So if you compare, right, so here I have written this g of x plus u is equal to g of x plus dg of x in the direction u. So I am just repeating it out here. So if you compare the two, then so comparing these two expressions here, so let us call it as 1 and 2. So by comparing 1 and 2, you will get, so comparing 1 and 2, what you will get is that d of g of t in the direction of alpha is equal to alpha times dg by dt. Or I mean, this dg by dt is the same as that d of g of t also. So that is the same as this particular thing here. Right. So so that is what happens in the scalar case here. Fine. Let us see here. So maybe what I will do is that I will give you some examples to show how this directional derivative is to be computed here. So perhaps that is the easiest way to show how to actually compute a directional derivative. So suppose let us take a function phi of v, which is equal to v dot v. Okay. So what I will do is that now perturb this function to v plus u, right? So that is exactly like this here, that g of x plus u is g of x plus the first order term. So this first order term will be the directional derivative, right? So here write this as v plus u. So this will be v plus u dot v plus u. Right? So this will be equal to v dot v plus this will be 2v dot u plus order. So let me first write it as u dot u. And now you can see that this is the first order term, and so that is the directional derivative in this particular case. So this is equal to phi of v plus 2v dot u plus order u. Right? These are the terms that are quadratic in u, so that we are just writing it as order of u, and hence the directional derivative in this particular case. So this implies that d of phi of x in the direction u is equal to 2 of this should be phi of v, I'm sorry, this should be phi of v, this is 2v dot u. So you have to note several things which are important in this particular case. So first thing is that what is the direction? Okay, so the direction will enter into the directional derivative, obviously. So this is the u. But what is important is that where are you evaluating this directional derivative? So that is also important. So this is the directional derivative of v in the direction of u evaluated at v. Okay, so you can see that where this directional derivative is being evaluated is also important, because that is also entering into this directional derivative. So you should not skip these arguments. Okay, so you have to write d of v evaluated at v in the direction u, and then that is the directional derivative here. So let us take another example to show this. So if I now have let us say a a tensor valued function. So g of t is equal to t square. So here I have taken a scalar valued function of a vector. Now this is a tensor valued function of a tensor. Okay, so this is another example. So here in this particular case, again perturbed, right? So as usual, g of t plus u now is equal to t plus u square, right? And then that you can write as t square plus tu plus ut plus u square. Here you have to be careful that because tensors do not commute, right? Tensor multiplication does not commute in general, so tu is not equal to ut in general, so you have to keep it as separate here. And now this is equal to g of t plus d of g of t in the direction u plus order u, right? So this u square term will be an order u term because that is quadratic or higher order compared to the linear term. So the linear term will be just the d of g of t in the direction u will be equal to tu plus ut. So that is how you will get that. So what you have to note is that it is linear in u. So that is as I said, that is the first order term in this expansion, and so that is always going to be linear in the direction. Okay, so always. So that is what you have to always bear in mind here. You can do it for t cube. So that I think I will leave it as a homework. Let us take another example. So suppose a phi of t is equal to trace of t now. Okay, so let us take this example. Then now if I expand this out, then phi of t plus u is equal to so trace is a linear operator. So what you will get that this is equal to trace of t plus u, which is equal to trace of t plus trace of u, which is equal to phi of t plus the directional derivative, right? So this trace of u. So in this particular case, we do not have those order u terms, right? The quadratic terms or higher order terms. So all that we have is this term here. So we will have that d of phi evaluated at t in the direction u is equal to trace of u. Okay, so here in this, for this special example, where you are evaluating this directional derivative is not entering, but in general it will enter, as the next example will show. So as I said, that it is very important to write where you are evaluating it and in which direction you are evaluating it. Okay, so both those things have to come in. Right, so maybe one last example for today. So that is the determinant example. So let us find out what is the directional derivative of the determinant. Right? So determinant of t plus u. So we have already seen this particular relation. So this is equal to determinant of t plus cofactor of t matrix inner product u plus t times cofactor of u plus determinant of u. So this relation we have already derived, and now this is equal to determinant of t plus cofactor t matrix inner product u plus order u. See, because this cofactor u, if you recall, cofactor of t had terms like t22, t33, minus something. So it was all quadratic, right? So higher order in u. So these are all higher order in u, and then this is the first order term, which is now the directional derivative. So in this particular case, your d of phi of t is in the direction of u is equal to, so here your phi of t that I am considering is equal to determinant of t. So for this particular thing, the d of phi of t in the direction u is equal to cofactor t matrix inner product t. So we will consider more complicated examples in the next class. So this, here I am just using the basic definition, right? I am just perturbing the quantity by some perturbation and then expanding it out. But once you come to more complicated tensor valued or vector valued functions, then it is better to have rules, right? Like just like in calculus, we have a product rule, we have a chain rule, and so on and so forth. So it will be better to have rules now for more complicated functions. So because I was considering very simple functions here, I was able to just expand it out and then write out the directional derivative. But that will not be possible when we are dealing with very complicated cases. And so we will need the product rule and the chain rule and so on. So that we will cover in the following lecture here. So we'll stop at this stage.